Now you might be wondering, why are these numbers so awkward to use? 6.02214076 times 10 to the 23rd for Avogadro's number. For R, 8.3144598. For Boltzmann constant, 1.38064,852 times 10 to the minus 23. They're all not simple numbers to remember, are they? So you might ask yourself, why are they not simple numbers? The answer is very simple. It's due to history and the way units were first defined. Now, for example, if I wanted to, I could define a new unit of temperature. Let's call it the bar. Okay? Now, if I say 1 bar equals 8.31 Kelvin, okay? 1 bar equals 8.31 Kelvin, then I would have R equals 1, okay? Water would then freeze at 32.87 bar. It would boil at 44.8 bar. I could then define another scale for my daily use. I call it shell bar. And I'll make my scale shell bar to equal the temperature in bar minus 32.7. So now I can have the freezing point of water is 0 shell bar, and the boiling point would be 11.9 shell bar. So now suddenly I can now say, okay, when I do my multiplications, R is just equal to 1. We could also define a new unit of mass. Let's call the new unit of mass the white. So that Avogadro's number is exactly 10 to the 24 and not this small little number that's slight off. You can see this again in this other example here. For example, because of the way they defined Avogadro's numbers, maybe I should make this bigger. We have mass is the mass or the molar mass constant is almost but not quite 1. Basically because of the difference in when they define the number earlier and then when they measure later. They find it ideally we could readjust the size of the NA so that this mu equals 1 rather than 0.99999999965. Again, the reason these numbers aren't exactly, or F could be an exact nice 100,000. Again, it's just because of the way we define our units that these numbers become so strange.